All right. Good morning, strength students. Welcome to week 4. Um, we had a little kind of a slowdown in week 3. There's a few assignments that got missed. There was just a lack of energy, is what I felt. So maybe that was quarantine on my end. I don't know. I'm sure the rain didn't help. We have lots of rain today. But on my walk yesterday, I had a good analogy for you, and it's a baseball analogy because I'm a baseball coach. Well, it used to be a baseball coach, so I'm not really doing much baseball right now. But we got to get good at this online thing because potentially we're online again next fall. So I got to get better at it. You got to get better at it. We can't miss assignments, though. We can't miss quizzes and we can't miss assignments. They kill us point-wise. So I did want to show you that. I have Blackboard up here, and I'm going to enter student view. And if you go into my grades, you can kind of see the setup. Now this is actually my grades. I gave myself grades. And you can see that we really only have 2 categories going. We have a homework category and a quiz category. That's it. We haven't had any midterms. We haven't had any finals. So these are important that we don't miss them. So here you can see I missed an entire homework assignment. I just missed it. Didn't turn it in, which is not what you want to do, guys. And I can say guys because you're all guys. And I missed a quiz. So these 2 things right here killed me, dropped me down to a high C. The grade to date is working. Hopefully you can see it. And you see the impact of missing things. So I don't know what happened last week. I need to know, so if you could let me know, do I need to send you reminders on the days that things are due? Like every Wednesday and every Friday we have assignments due. And then we have a quiz on Fridays. It won't be every Friday, but it has been the last 2. So, and they're just on Fridays. I don't want to run them over the weekend or I can't get them graded. Like right now, they're not graded because I had to reopen it and let them come in till Sunday night. So, which I'll do. I mean, this is an unusual situation, so I'm willing to do that. But don't miss stuff. That's not going to work. All right, let's talk about Poisson's ratio. First, I'm going to finish up Chapter 10, the stress strain curve, and just emphasize a few things. So I'm going to say bye to you all right now, maybe. And just go with the tab. I kind of have it off to the side. I got some weird shadows because I have some lights on, but I'm sure we can handle it. So let's just it's super important that we understand the stress strain curve. Strain usually is down here, stress is up here, and this is the tensile test where we get the material properties. So material properties are things like E, Young's modulus, mu, Poisson's ratio, which we'll do today, the thermal coefficient of expansion, which we'll do this week, multiple material stress and strains we'll do this week. So all of those are material properties, and those material properties come from a tensile test, typically. So in a tensile test, we load it. We did this last week. We put load on, and this is essentially load because the area, we know stress is P over A, and the area doesn't change, right? The cross-section area does not change. So what we're doing is we're raising the P value, the load. And that, of course, raises the stress. And here, as the strain goes up, we know that strain is delta over L. The original length does not change. It stays the same. What changes is the delta. So really, this is a graph of the load and the change. That's really what the graph is of. We just call it stress strain because those 2 values are the values we use to make the comparison when we're designing or when we're analyzing. All right, this first region where it comes up and then it hits the proportional limit. Remember, the proportional limit is here at the end of the straight line. So first we hit the proportional limit, then it curls over and we hit the yield point. That's usually called the upper yield. And then we maybe have a lower yield, depending on the material. Not all materials have this beautiful curve like mild steel does. Then it comes over to the strain hardening area, and then it hits the ultimate strength, and then it fails. Right? So that's our stress strain curve. What I want to emphasize is the Hooke's Law region, is from the upper yield back, and this is called the elastic region. This is the region that we want to work in, and this is the region, the only region of the graph that E is valid, that mu is valid, Poisson's ratio, which we'll do today, that thermal coefficient of expansion is valid, all only in this region of the curve. If we are outside of this region, and we know this region, because we can calculate stress with P over A. We can calculate that stress, right? And we can see, and look and see, is it in the elastic or is it in the plastic region? That we should be doing first on every problem, because we cannot predict the elongation. We cannot predict the Poisson's ratio transverse change. We cannot predict anything about thermal expansion if we are in the plastic region. This is a no-go area. All right, there we go. Stress strain curve emphasized. So you have a homework problem out of the chapter 10, one more of them, where you have to calculate some stresses. A little bit like your quiz. All right, let's talk about Poisson's ratio. It's a fairly easy concept, but it gets complicated with strain, because not a lot of students really fully understand strain. So let's remember what strain is. If I have, let's say I have a piece of mild steel, and I have it welded to a plate, and I'm going to push on it with 40,000 pounds, a whole bunch of weight, right? And we'll say that this thing is 1 by 1, and it's a square shape, and it's solid, 1 inch by 1 inch, right? So we all know we can calculate the stress, and that's what we should do first, is calculate P over A, just to see if we're still within Hooke's law, right? So 40,000 pounds divided by 1 by 1 equals 40,000 PSI. Everyone follow me on that? That is 40,000 divided by the area, which is 1 inch squared. 40,000 PSI. I haven't talked a lot about the charts in the back, so I want to do that. This is what, let's say we want to know the elongation. That's our end goal, is like, how much did this deform, right? First thing we want to do is check and see that it's within the Hooke's law region. The region is defined by the yield stress. So let's go look at the yield stress. In the back of the book are typical average properties of some common materials. Yeah? Everyone see that? Looks like it's page 501. And in this, we can look up materials, and we can get material properties, E, G, which we have not talked about. Tensile yield strength, we have talked about that. That's the upper limit to Hooke's law. Ultimate strength, that's where the curve rolled over, way up past the permanent deformation in the plastic region. And then we have thermal expansion, and look at Poisson's ratio. Material property. I said we had mild steel, so that's this, A36. And the 36 stands for 36,000 tensile yield strength. 36,000 for A36. Well, let's see what we have. Right? We have 40. So the curve, which goes like this, right here is 36 KSI, 36,000 PSI. And that's where we can do all of our forecasting, under 36 for mild steel. This is A36 mild steel. Right? And we have 40. We are in the plastic region. We are outside of Hooke's law. We can do nothing else. That's how it works. That's how and why we check it. Okay? All right. So I want to continue this problem. So I'm going to change the load so we can actually do it. Right? So I'm going to change this to 30,000. Now I am 30,000 PSI, and I am down in here somewhere within Hooke's law, meaning that the material is predictable, and I can make some predictions. All right. So what Poisson's ratio does is it gives us the amount of transverse change. This is transverse. This is along the long axis of the part. And so that's what we call elongation, or that's our delta that we calculated before. So Poisson's ratio, this transverse, this axial along the long axis, this is what we've calculated in the past. And strain, remember, strain is just permanent or non-permanent deformation. So it allows us to predict what is going on in the change. So strain axial is what we've calculated. That's how much it stretches. So if I take my pen and I stretch it, tunk. Oh, that was too much stretch. Right there. Stretch, right? Axial. When we pull something apart, when we stretch it, that stretch has to come from somewhere, and it is the cross-sectional change. That's transverse. Poisson's ratio gives us that. If we can calculate the axial, and we can look up the material, if we know the material, then we can determine how much that cross-section changes. And we can calculate a new stress, because if the area gets smaller, the stress goes up, right? All right. So that's Poisson's ratio. That's why we use it. It's a very small number typically. Poisson's ratio is very small. First of all, elongation typically is very small. So that means that the cross-sectional area changes a little bit. But it's relational as long as we're within Hooke's law. All right. So let's continue here. Can I just minimize that? Oh, maybe. Oh, no, can't do it. I'll get rid of me. I'll be back. All right. So let's calculate this. The first thing, if we want to know how much it changes in the cross-section, the first thing we have to know is how much it changes in the axial long axis. So how did we get that before? Well, we know that E equals, what does E equal? Anyone remember? Stress over strain. And what does stress equal? P over A delta over L. All right. This is our axial strain. If I can calculate this, then I can move forward and go for the transverse based on this relationship, because I know this. If I know the material, I know Poisson's ratio. So you can use this formula if you know the material and you know the stress. I do. So I can say, oh, my axial strain is going to be stress over, and this is compressive stress, right, because I'm pushing on it, over E. So I need E for mild steel. And where do you think I get that? I get it from the back of the book. So if you know the material, you know a lot of things. You might want to tab this. I got it tabbed here. You know a lot of things about your formulas. And in this case, I know E is, for mild steel, E is 30,000. And Poisson's ratio is 0.25. So those are both pieces of information I'm going to need. 30,000, 0.25. Notice that it's 30,000 KSI. Holy cow, this is huge. This is 30 million PSI. Different than yield, which is 36,000 KSI. You might need to pause this now and then and just process this, because I'm throwing a lot of numbers at you that I know really well and that you do not know really well. So, modulus of elasticity is a very big number. Young's modulus, 30 million PSI. Poisson's ratio, 0.25. All right. So let's capture that. I know I have an E of, I'm just going to write it 30 E to the 6 PSI. Remember, it's 30,000 KSI. And then Poisson's ratio is just 0.25, and that's unitless. No unit on Poisson's ratio. All right. So how do we do this? Here's the E. We plug it in here, and we can say the axial strain is equal to our stress, 30,000. And you do want to make sure you're in the same unit, PSI, over E, 30 million PSI. And there's a lot of zeros there, so I'm actually going to calculate it. I have a feeling it's like 0.001, but yep, 0.001. Remember, the unit of strain is inches per inch. It's how much change we get per inch. Inches per inch. That's along the axis. And since we're compressing, this is actually a decrease. Decrease in length per unit inch, 0.001. If I wanted to know the full change, I'd have to have some kind of distance like 15 inches. And then I could calculate the total change. Okay? That's how we did axial strain. Now, Poisson's ratio is going to give us how much this increases or decreases cross-sectionally. And in this case, it actually, when you push on something, it gets bigger, so it increases. So, and the only way you know that is just by observation, right? And there's no sign that tells it plus or minus and all that kind of stuff. You just got to know it by looking at the system. So we know that if we push on this, this thing's going to get fatter. Poisson's ratio is the relationship between the transverse and the axial strain. And I know Poisson's ratio is equal to 0.25. So if I can calculate axial strain, which I just did, 0.001, I can get transverse. And it's a multiplication. The transverse strain is equal to the axial strain times Poisson's ratio, 0.25. Transverse strain equals. So it gets smaller. It's 0.001 times 0.25. 0.00025. It's always very small. That's how much the change is. Now, that doesn't give us a dimensional change, right? That just gives us the transverse. But we know the transverse is equal to what? What was it equal to? Delta over the original length. And if I want to know the actual dimensional change, I put in the original length, I calculate a transverse, right here, transverse, and I can get the actual delta change, which is going to be L. I said this was 1 inch by 1 inch, so original length is 1 inch. And my transverse that I just calculated with Poisson's ratio is 0.0025. So the actual change is 0.00025 inches increase because I'm squishing it. And it goes, right? Increase. And that's the delta, like, you know, it was, here, I'll show you, like, it was like this, right, when we're pushing on it, and now it's like this. This is an exaggeration. Right, we push on it, it gets fatter. So this becomes my transverse strain, which gives me my delta in the transverse. So this is the total increase. It really is, you know, half on each side, but it goes from 1 inch to 1.00025. You're thinking, that's not very much. That's true. Not very much. Absolutely not very much. But it's important, especially when we stretch things and that area gets smaller. If you're designing near the yield, it can push it over the yield. All right, that's enough for sure. Happy week 4. Communicate with me. Let me know how things are going, and if you need anything. I don't really, you know, we had 4 people miss the quiz. 2 of you have communicated with me, so we've worked that out, but 2 of you have not, and I just need to know what's going on. And even for those of you that did not miss anything, you know, if it would be helpful for me to send you a reminder email, I can do that every Wednesday and Friday to say, hey, you know, you have an assignment due today, you have a quiz that's available today, whatever you need, just let me know. I don't want to open it up for the whole weekend. I think that's not scheduled enough, I guess. So, and it doesn't allow me to do the grading I need to do. So, all right. Take care of yourself. Wash your hands. Stay diligent with this. This is the 4th inning of a long baseball game, and that's usually when players fall asleep. It's true. Like, you lose your mental focus. So you get it back towards the end of the baseball game because then there's new energy to try and win this thing. You have all your focus at the beginning of a game because you want to be a high performer and you want to get ahead in the game. It's the middle part that's really hard to focus through, and I've felt it too. So refocus yourself. It's a good time to go to school. Tell your friends it's a good time to go to school. When we come out of this current economy, it's going to be booming. There's going to be lots of opportunities. It'll be a great time to get a degree. So anyway, hang in there. Good job, and be well.